Hey everybody, it's Mrs. Harbin. Welcome to Chemical Reactions, Video Notes 5.1. So we're going to be trying to do 4 things here, and it's all about taking these chemicals we know about in this chemical language and explaining it. So, hey, it's in chapter 11 of your book. Recognize that? Yeah, it's your book. Okay, so read chapter 11, section 1. So we talked about this in class, but what do we think happens when a chemical change happens? Well, we have to make some observations. So if any of these things happen and a new substance forms, that's the key. These are some signs that a new substance is forming. Okay, so all of these except the precipitate happened when I put the sugar and the sulfuric acid together. You saw this happen. This is a precipitate. Precipitates in a solid form. Okay. So, what's in a chemical equation? It's an equation that uses symbols to represent a chemical reaction. Hey, look at that sugar. What does your body make? It makes sugar during cellular respiration. Okay. So, So here are the reactants. Here are the products. So chemical change changes reactants into products, and these have totally new identities. Okay, so which ones are which? Reactants are the substances that are used in the chemical reaction. They're used up, they're the starting materials, they're what you put in. Products are what comes out. Okay, so they are made in a chemical reaction. Remember that the arrow points to products. So hey, label the reactants and products. See if you can do it this time. All right? Also, in a chemical reaction, there are lots of symbols. So if you see the symbol of parentheses G, it's a gas. It comes after a gas. L for liquid, S for solid. AQ is for aqueous, which means dissolved in water. Dissolved in water. Plus sign means reacts with if it's on the left side, if it's on the reactant side, or it means and if it's on the product side. Down arrow is precipitate product, which we would also put an S for. Up arrow is a gas as a product. And this arrow is the arrow in between reactants and products. It means to produce or to yield. Sometimes we have things over the arrow in a chemical reaction. It's called a catalyst. All right, so let's take this reaction and translate it. So let's put it into words. So what we're finding out is we have to know how to name this. We're going to call it calcium oxide. What kind of calcium oxide? Solid. Solid calcium oxide. Reacts with, I put oxide, what was I thinking? Reacts with gaseous hydrogen to produce, hey, where'd I get that? That's the arrow, to produce aqueous calcium hydroxide. All of that naming comes in handy. You could also say to produce a solution of calcium hydroxide. So we just took the balanced formula equation and turned it into words. Just a reminder, if you look back in the reaction before, when you see H2, you think hydrogen gas. Here's a word that you should remember. I know it's not really a word, but it is fun to say, because these represent the 7 diatomic elements. These elements are never alone if they're by themselves. They always pair up if they're by themselves. All are gases except bromine is a liquid and iodine is a solid. I can't remember which ones to do. Well, they start with the element number 7 on the periodic table. They make the number 7 and they point over to hydrogen as the 7th of the super 7 diatomic elements. Now, you only have to put the 2 next to them when they're by themselves in a chemical reaction. If they're in a compound, you don't put the number 2 unless you need to cancel charge. Okay, so hey, this will be us in class. You can write it down, you could try to translate it, and we'll go over it in class. All right, hey, can we go the opposite way? Yeah, look, here are the words. We can change it into a chemical reaction. So let's analyze it. We know we're going to have a solid in there, we're going to have a gas in there, and we're going to have a solid. So we're going to put the parentheses tell everybody what state of matter they are. Reacts with is a plus sign. To produce is an arrow. So we can get going. Solid magnesium, symbol Mg. Guess what? You get a periodic table. Reacts with oxygen gas to produce magnesium oxide. Now, when you're doing magnesium oxide, we look at the periodic table and we look up magnesium's a +2, oxide's a -2, so you get MgO. Alright, I did something wrong here, and I did it wrong on purpose to point it out. When you see oxygen gas, you might be thinking, oh, oxygen gas, oh. But remember the super 7. Right now, oxygen's by itself. So is it really by itself? No way. Anytime the element oxygen is in a chemical reaction, it is O2 gas. All right. So the only thing missing here are something we call coefficients. I'm going to put them in, and we'll talk about them later. Okay. But now this is the chemical reaction that represents the word equation. Hey, look, it's another one. You try it, and we'll check it in class. All right. We talked about this already because every time a chemical reaction is done, the amount of mass of reactants you put in is equal to the amount of products that come out by mass. Reactant mass equals product mass. Now, this has been observed over and over and over in science, so it's considered the law of conservation of mass, meaning atoms, the mass is not created or destroyed in a chemical reaction. So the thing that must be happening is that the atoms are making new bonds, but they all have to be there. Looks like he's thinking about it. So we balance chemical equations. And by balancing, I mean that whatever goes in must come out, and you can't lose any, you can't gain any. So if you put a purple and 2 green in, and they make something new, like this guy, you better be able to count 2 green and a purple on this side, even though they're bonded together differently. It has to stay balanced. So if I put some propane, propane gas right here. Oh, that's Pidgey. Reacts with oxygen gas to produce carbon dioxide gas and high temperature water gas. You have to count everything that goes in. 1, 2, 3. 1, 2, 3 carbons. But guess what? Here they're attached to hydrogens. Here they're attached to oxygens. New identity, carbon dioxide. Right? And look at all these diatomic oxygen molecules that are reacting in this reaction. Okay, but there's 2, 4, 6, 8, 10 O's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 O's. Get out! Not kidding. They're all there. Love conservation. So, we have to talk about how you can count the atoms to make sure they're all there. So there are going to be subscripts. Subscripts say it low so it goes low. Subscripts go low. Subscripts go low. It tells you how many atoms of that element are in the compound. So C2H6 is made of 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens. All right, but you have to put them as subscripts because they're all stuck together in that molecule. Okay, so you can look at compounds and figure out how many atoms there are. So if you look at CO2, you're going to begin 1 carbon atom and 2 oxygen atoms. This one's a little tougher, but don't be fooled. What this means is that there are 2 NH4s. So I could rewrite this if I want. NH4, NH4, there's 2 of them. CO3, there's 1 of them. And so now we can look at it again, and there's actually 4 plus 4, 8. Hey, who forgot to ask about hydrogen? We got nitrogen, we got oxygen, we got carbon, and we got oxygen again. Come on, Harbin. I was just talking to myself, and then I almost wrote Harbin. Hydrogen, we'll change that to hydrogen. How many nitrogen? Well, 1, 2 nitrogen atoms. How many hydrogen atoms? 8 hydrogen atoms. Carbon, 1. Oxygen, 3. All right. I'm going to let you do that one, and we'll check it. Boom. Okay. Coefficients. So these numbers down low, subscripts go low. All right. Coefficients are multipliers. Coefficients are multipliers. They're put in front of things to tell you how many times that whole thing is in that chemical reaction. So a 3 in front of something means 3 of the x's. All right. So there's no number here. That really means there's a 1 there, and there's a 1 there, and there's a 2 there. So those are the multipliers to multiply how many times those compounds or elements are in the reaction. So now we're going to do the same thing we did before, except we're going to use the multiplier to help us. So this means 2 of the CO2s. So if we wanted to take that out, we'd have to put that in because we need 2 of them. So how many carbons? I see 2. How many oxygens? 4. That reminds me of like when you're standing in line at Walgreens. So like, I see 3 if there's 3 people in line. I don't know if that ever happened to you, but it has happened to me. Oh, look, I see 3. 3 what? 3 of these whole things. We got NH4 2CO3. NH4 2CO3. Hey, guess what that's called? Ammonium carbonate. Who forgot that? All right, so there's 3 of these. That's what that multiplier meant. So now I have 1, 2, 3 carbons. I have 3, 6, 9 oxygens. I have 2 nitrogens plus 2 nitrogens, 4 nitrogens, and then I have 8 hydrogens. But oh wait, I forgot. Did I just forget something? You bet I did. 2, 4, 6 nitrogens. 8, 16, 24. What? 24 hydrogens. Okay, so there's 8 from that one, plus 8 from that one, plus 8. 8 times 3. All right, I want you to do this one, and guess what we'll do? You said it, check me in class. All right. So now that we can count all of that stuff, we have to use coefficients to balance chemical equations. And we use an atom inventory to help us. Right? You don't have to write it out, but it really does help. So I know I'm going to be looking for some H's and some O's in this reaction. When I start, I have 2 H's and 2 O's. And I have 2 H's and 1 O's. It is not balanced. So the only way we can balance is by putting in coefficients. Because we can't change the identity of a compound or an element. Hydrogen is H2. I can't go writing H3. Nuh-uh, because it's H2. So if I want this to balance, I have to use a coefficient. I do not have enough oxygen on this side of my reaction, so I'm going to put a 2 there. Once you put a coefficient, you don't add it to this. You cross this out and recount. So now I have 2, and then I have 4. Row hydrogens are not balanced. So I go to my reactant side. I need more hydrogen. So instead of leaving a 1 there, I'm going to put a 2. I don't add to this number. I cross out this number and I redo it, and now I have 4 hydrogens. 4 hydrogens, 2 oxygen, 4. Yeah, it's balanced. You betcha. It's balanced. Okay, let's try it again. N's and H's. Right now I have 2 N's on the left, 2 H's on the left, 1 N on the right, 3 H's on the right. So this is my atom inventory, and now I see it's not balanced. So I need more N's on this side. How many? I need 2 N's. So if I put a 2 in front, I have to multiply by the whole thing. But I don't add to these numbers. I cross these out and I count all over again. So now I have 2 N's and 2 times 3 is 6 H's. All right. That is not balanced. So I got to go back to my reactant side. And N's are fine. Don't mess with the N's. I need some more hydrogens. I need a total of 6. So if I put a 3 here, 3 times 2, remember, don't add to that. Totally count it again. Hey, look it. It's balanced. Oh, happy face. Show ya. Show your face if you're happy. Woo. Okay. So let's review. Coefficients are the numbers that go in front, and they're multipliers for chemical reactions. Reactants are on the left side of the chemical reaction. Products are on the right. The reason you have to put coefficients in is because you can't lose or gain any atoms in a chemical reaction. They all have to show up. Now they rebond. Okay, so this was being held together by a covalent bond between 2 H's. This is being held together by a covalent bond between 2 oxygens. This is being held together by a covalent bond between hydrogen and oxygen here and hydrogen and oxygen there. We actually have 2 of those. Whoa, isn't that the best water thing? 2 of those. Oh, why am I drawing 2? Please stop me. Come on. Just 1 of those. See how the coefficient? You don't see it, so it must be a 1. And then 2 of these. That's an H, isn't it? Yeah. H, H, H. Right, so 1, 2, 3, 4. 1, 2, 3, 4. But when they're reactants, they're different identities than the products. Okay. Hey, did I mention looking at chapter 11? Section 1 and 4? I hope I did. All right, it's been fun. We have to do all of these things and we look at a chemical reaction. All right, peace out.